All right, since I'm not going to be here, I wanted to try to be the best I could at being here and record this video for you. So we're going to talk about projectile motion and the concepts of projectile motion. A projectile is anything that is launched through the air and is only under the influence of gravity once it's in the air. So there is no rocket booster on it, there is no parachute on it, there's nothing like that. It's just flying through the air under its own inertia, its ability to keep on moving. So the only force acting is gravity, and gravity only acts vertically. So we're going to build on what we already know in terms of free fall and object falling, then we'll build in the horizontal component to it for when something is thrown through the air. So what we know already is at the highest point of an object in the vertical direction, vertical we're only talking right now, the initial velocity is 0, and that as it falls, it will gain speed at the rate of 9.8 meters per second every second. So for 1 second it's going 9.8, 2 seconds 19.8 or 0.6, and continues that way all the way down through its fall. We know that the amount of distance that it's going to cover each second will get longer and longer as it accelerates down, and the velocity will get greater as it falls. So when we're identifying our givens for all projectiles, what we know is that vertically in the y direction, remember like on a graph, y goes up and down, x goes side to side or horizontal. In the vertical y direction, we know the initial velocity is going to be 0 meters per second because we're only moving horizontally to begin with. And that the acceleration then will be 9.8 meters per second squared unless I tell you to use 10, in which case you'll use 10 instead of 9.8. Remember, the valuation of gravity, acceleration in the y direction, is going to be 9.8 in the lab or approximately 10, what we'll use for most problems when we solve them on worksheets, on quizzes, on tests, those kind of things. So we know these two are givens automatically. We know the final velocity is going to be higher than the initial velocity because it's going to gain speed at this rate. D is generally known as the height. Distance in the y direction is the height of an object. So when we tell you an object is shot from a height of 10 meters, that would be your dy. Time is typically something that you're going to have to solve for. I'll write that a little bit neater. Usually the way you solve for that is using the equation that we already know, 2 times the distance in the y direction, since we're dealing with the time it takes to fall, divided by the acceleration in the y direction. Again, that's a formula you're already familiar with. The equations that we use vertically are VF equals VI plus AT. This is all the vertical information only we can use. And that distance in the y direction, the height, is 1/2 times the acceleration of gravity times time squared. An equation we already know. And then there's the manipulation of that equation, t equals the square root of 2dy over a y. The height divided by gravity, 2 times the height divided by gravity, square root of that is the time. So that's the information that we need vertically. So the next thing to do is add in the horizontal component as something is thrown or launched or shot through the air. I'm going to pause the video, get set up for part 2. Okay, part 2. Now this is flying through the air now. It's not just dropping straight down. It's not only in free fall. So something has launched this thing forward, and so now as it launches forward, it will have an initial horizontal velocity, velocity in the x direction. Once it's launched through the air, nothing is pushing it forward, nothing is acting against it, so that velocity stays the same. So what I know in the x direction is that my initial and final velocities are the same, and therefore I have no acceleration, 0 meters per second squared, in the x direction, because nothing forces it to change the velocity. If the velocity were to change, there'd be an acceleration. No change in velocity, no acceleration. So let's take a look at what happens. Let's say this thing is launched with a velocity of 10 meters per second. We'll just throw that number out there. In the first second, it will fall a little bit as it gains some velocity from acceleration of gravity. And the next second, it will continue moving at 10 meters per second horizontally, but it will fall a little bit farther vertically. It will then move its 10 meters per second and fall a little bit farther vertically. And this continues to happen all the way down. If we look at every second where the ball travels horizontally by the same distance each second because it has a constant velocity, but then falls at a greater rate each second. And when that happens, we end up seeing this parabolic shape, this curved shape that we're used to seeing as a projectile comes to the floor. So here's what we know again. The velocity doesn't change horizontally because nothing causes it to accelerate forward or slow down. Therefore, A is 0. The other thing we know is that when this thing lands, it's no longer a projectile. So whenever it lands vertically, it lands horizontally. It lands. So we know that these two values are the same. So oftentimes what we'll have to do is solve for the time in one of the two areas, X or Y, and then use that same time on the other side. We have to bring them back and forth. And usually you'll start with the height to solve for the time, to get the time for solve for how far this thing will travel, which is known as the range, the horizontal distance. So in the x direction, the only equation that we have is that the range, dx, is equal to the velocity in the x direction times the time. D equals v times t. Again, an equation we already know. This is it. These are your notes. This is all the information you need to be able to go forward and solve the problems. Now the next step that we're going to do, now that you have all this information, is we're going to go to part 3, where I've done a little bit of work to see if we can predict how far the launcher that we've used before is going to send a projectile horizontally, and we got a little work to do for that. So part 3 coming up next. All right, so over here is the launcher we've already used in class. And we already established that the velocity it shoots at is 6.7 meters per second. So that's the horizontal velocity it's going to come out of here at. I measured the height from the floor to the bottom here where it launches, and I got that information as well. So here's what we know so far. Coming at you. We know that horizontally, our velocity is 6.7 meters per second. That is our initial and our final velocity because we have no acceleration. We also know that there is no vertical velocity because it's only being shot horizontally. The height, again, is 1.105 meters, and that gravity is 9.8 meters per second squared. The goal is for us to figure out how long it's in the air to determine how far it's going to travel. And if we do this correctly, it will land right there in that note card. So here's what we have to do. Time is equal to the square root of 2dy over ay. That's the square root of 2 times 1.105 divided by 9.8. And when I do that math, that will give me the time, and that time is the same in both x and y direction, because again, when it lands, it lands. I'm then going to use that time with the horizontal equation, vxt. So I'll have 6.7 times that time. So let's do a little math here and figure this out. On my calculator, I've already done that the square root of 2d over y over a is 0.47 seconds. So 0.47 seconds in both directions. So now, as I multiply the horizontal velocity times that time, 6.7 times 0.47, I get 3.18 meters. So the distance this should travel is 3.18 meters. Now, I've already gone through and measured out 3.18 meters from the edge of the table to where this note card is here. So if my calculations are correct, and you can do them if you want to see if I did them correctly, but if my calculations are correct, when I launch this thing, it should land on the note card or maybe a little bit left or right, but it should go about that same distance. Hopefully we've done this correctly. If not, this is the only take I'm doing, so then we'll talk about why I was wrong. So here we go. 3, 2, 1, launch. Just a little bit left. We had the right distance, just some bad aim. It landed right here. Now your job is in your packet to start working on how to solve these problems. And I will have information up on the classroom for you with solved problems and solutions so you know what to do. Enjoy.